so we're going to go ahead and start talking about torque, which is the next section. But before we can get into that, we need to talk about the two different kinds of motion that there are. And we've already actually talked about one of them, you just didn't know it yet because we didn't call it translational motion. But everything that we've done so far in this class, motion-wise, has been translational motion. That means that we're either moving in the x direction, or we're moving in the y direction, or we're moving in the z direction. So it is a sliding type of motion. And so, like a box sliding across the floor, or a car driving down the road or something like that, any of that would be translational motion, okay, moving in one axis, all right? Rotational motion is something different, all right? And that's where we're going to pull in our circular motion. That's just another name for it. So rotational or circular, or we can even call it angular motion. Okay, so any of those is referring to the second type of motion here. And this second type of motion is caused by torque. Now, notice translational motion is caused by a force. Force is the ability to make a change in direction or cause an object to accelerate. And then a rotational motion is caused by a torque. And so torque is kind of the counterpart to force. It is a rotational force. It's able to cause a change in the angular acceleration or cause circular motion of an object. Okay, so force and torque are counterparts to each other. Okay, all right, so let's look at the definition for torque here then. Okay, it is the ability of a force to cause an angular acceleration alpha. And the symbol for torque is the Greek letter tau, which kind of looks like a capital T, but it's kind of curved there with a little curvy top. It's weird. All right, so there's the correct symbol for torque. All right, so here's your box equation, which means it's going to be given to you on any quiz or test. All right, it says that tau, or torque, is equal to force times lever arm times the sine of the angle theta. So let's talk about a few of those things real quick. First off, the force that we're interested in will be the force that causes torque. Okay, there could be multiple forces acting on an object, but only one or two or forces would actually cause the object to have an angular acceleration. You could have a force that doesn't cause the object to rotate. Maybe it causes the object to slide in translational motion. That would not be one of the forces that you would plug into your torque equation. Okay, the next one, D, is the lever arm. And up in the equation, I have a lowercase d, so let's kind of stick with that. So lever arm is what D is called, and that is the distance from the force to what we call the axis of rotation. That's the point about which we will rotate. And then theta. Theta is the angle between the force vector and the lever arm vector. And yes, they are vectors, so we need to know that. All right, and then since the torque equation consists of two variables that are vectors, force and the lever arm, that means that torque itself will also be a vector quantity. All right, so let's see if we can't plug in some stuff. All right, so we have this example here of a door, and this point right down here, this is our axis of rotation. That means that the door could rotate in this direction, or it could rotate in that direction, right? It's free to swing around the hinges down here, okay? All right, so the question says, rank the forces shown above from largest to smallest amount required to cause a torque on the door, and give a brief explanation of why, okay? So we're trying to figure out, like it says here, from largest to smallest amount of force required to give the same amount of torque, or cause the same amount of rotation in the door, okay? All right, so we're going to use our torque equation to help us do this. So I'm going to bring that back out here. Okay. All right, one quick thing I think I want to touch on is theta. All right, let's look at that term for theta. And it was the sine of theta. So let's look at a sine curve, something like that, okay? All right, so up here, this is going to be the value 1, this is 0, and this is negative 1. And what we're doing is we're actually following the unit circle, okay? And remember that sine corresponds to the y-coordinate, all right? So over here at the side where we have 0 degrees, the x and y coordinate, of course we know x comes first, y comes second. If I were to move over to this point, I would have an x position or an x value of 1, but I didn't move upward any when I came over to 0 degrees, so my y value is going to be 0, all right? So when x is equal to, or excuse me, when theta is equal to 0 degrees, you get a y value of 0. And I'll put 0 degrees right there, okay? And then if we rotate up here to this position where we've got our 90 degree, what would happen to our x and y coordinate, okay? Well, I didn't move any off of the origin in the x-axis, so we know that my x coordinate is going to be 0, and my y, I will have moved up to 1, okay? The reason they call it the unit circle is because every time you move over on the unit circle, it's 1 unit, okay? All right, so if I'm up here at a value of 1, then that means that this must be 90 degrees down here. Okay, let's keep going. If I come over to this position where I'm looking at 180 degrees, then I will have moved to -1 in the x-axis, but I'm not up or down at all from the origin when I'm right here in the y-axis. So that means that we're going to get a value of 0. So here it'd be -1 and 0. So right here, when I'm back at 0 again, that must be 180 degrees. All right, then we're going to move down to this position. So we're at 270. And when I do that, I've moved down -1 in the y-axis, but I haven't moved left or right from the origin, so my x coordinate would be 0. So I would have 0, -1. That means that right here, when I'm at -1, okay, this must be 270 degrees. And then finally, I can come back up to this point where I've come all the way around the circle, so that's 360 degrees. And my y value is going to return to 0 again. Okay? Now, we just did this all in terms of degrees. Of course, when we do angular motion, we always put things in terms of radians, right? So we know that, at the beginning, we're starting out with 0 radians. When we move to 90, we can say that's pi half radians. Then we get to 180, and that's pi radians. Then we've got 3 pi half radians. And then finally, we have 2 pi radians when we make it all the way back around to 360. Okay? So those are your radian values. And then on top, we have our angular values. Now, why did I even bring this up? Why are we looking at the sine graph? Well, the reason I'm having you look at it is to look at these values that get returned when you take the sine of any of these angles. Notice, please, that the maximum value that you can have on a sine curve is 1, okay? So 1 is the maximum value you could possibly get, okay? And that's going to occur at 90 degrees, all right? If you are anything less than 90 degrees or you're anything more than 90 degrees, you are heading away from the maximum value of 1. So if we look at that in our torque equation over here, and we see that our torque equation has this term sine theta, that means that if you have a theta equal to 90, if theta equals 90 degrees, then you have a maximum torque. Okay? If theta, like I said, if theta is anything less than or more than 90 degrees, then you will not have a maximum torque value. Your torque value is not as large as it could be if you change the angle of the force to 90 degrees. Okay, so now let's see if we can't come in here and rank some of these things. Let's look at force vector 2, okay? So the lever arm is the distance from the axis of rotation to the force vector. So right here, that's going to be the lever arm for force 2, okay? And here's the force vector for number 2. So according to the definition for theta, that is the angle between the lever arm and the force vector. So that's going to be 90 degrees. So we do have a maximum potential there. But now let's look at both of these other components, the force and lever arm. We have a very small lever arm. Okay, it's very short. We are extremely close to the axis of rotation, and we have this force value here. Now, do you think that we're going to have a very high or very low force value to compensate for this very short lever arm in order to get the same amount of torque or rotation in the door? Okay, hopefully you said that we're going to need to have a pretty large force vector because the lever arm term is small. Okay, so and we're going from largest to smallest. So force 2 is going to be pretty high on our list when we're ranking these. Okay, all right, let's come down here and look at the next one. Let's look at force 1. Okay, all right, so force vector 1. The lever arm is the distance from the axis of rotation all the way out to the force vector. Here's the force vector we're concerned with, force vector 1. All right, and the angle between those two is theta, and that's 90, so that's a maximum angular value there. So we really only have to concern ourselves with the force and the lever arm. Now I've got a really large lever arm value, so would we need to have a large force value to get the same amount of torque, or would we need a smaller force value to get the same amount of torque? All right, hopefully you said we needed a small value, so let's put it down here on our list somewhere. Okay, let's do another one. Let's look at force 4 here, okay? So in this case, our lever arm is, again, from the axis of rotation all the way out to where the force is being applied. So that's the entire length of the door, so that's a really long lever arm. Now, our force vector is pointing in this direction. And so what's the angle between those two? I think those are, if our lever arm vector points this way and the force vector points the other way, then that means that the angle between those opposing arrows is going to be 180 degrees. Okay, so let's go back over here to our sine curve real quick and look at the value of sine when we're at 180 degrees. That's 0. Okay, so if we look at our torque formula there, the sine of theta when it's 180 degrees is going to be 0. That means you're multiplying these things by 0. So how much torque are you going to get? 0. So does that mean that is that going to be pretty high on the list, or is that going to be pretty low on the list? Okay, if we're ranking the forces from largest to smallest, and we know that we're going to get 0 torque, then that's probably going to be pretty low on the list. All right. And I guess if you wanted, I guess you could say it would need to be high on the list or take it out of the list completely, because there's not going to be any torque caused at all by that one. Okay, so that one's kind of a little tricky. So I'm gonna put it down here. It doesn't really matter. That force doesn't really factor into anything at all anyways. Okay, now let's look at number 3 here. Okay, so here's force vector 3, and let's see, our lever arm, the distance from the axis of rotation all the way out to the force that's being applied. There's our force 3, and the angle between those two is the one that we're concerned with here. Okay, now this angle is obviously something larger than 90 degrees, which means when you take the sine of that angle, are we going to get a maximum possible torque value? No, we're not. It's not at 90 degrees. Okay, so let's look at that lever arm. That lever arm is exactly the same as it was for force vector 1. So if we're looking at our equation up here, and we're trying to see which force needs to be higher or lower, we don't have a maximum value. The lever arm is the same as it was for force vector 1. So are you going to need force 3 to be larger or smaller than force 1 to get the same amount of torque? You're going to want it to be larger. Hopefully you came up with that. All right, that kind of compensates for your theta not being at 90 degrees. Okay, so force 2 has to be your largest, then force 3 comes next, then force 1, and then force 4, we said, really causes no torque. Okay? All right, let's talk about units of torque here. Again, let's look at our formula. We've got force times lever arm. Lever arm is just a distance, okay? So if we're going to come up with units out of here, we know that force is measured in newtons. We know that a distance of something is measured in meters. And when you take the sine of an angle, you simply get a value, and that value is a unitless number. So that means that our correct units for torque are called Newton meters, which is newtons times meters. This does not get renamed into a new unit, and I say that because typically in physics, when you have some kind of a compound unit like this, it usually gets renamed into a single unit so that it's easier to keep track of. But there are actually 2 things in physics that have units of Newton meters. One of them is a vector, that would be this one, torque, and the other one is a scalar, and we'll talk about that one later on. The scalar one gets renamed into a new unit, and so we keep torque as Newton meters so we can distinguish between the two. All right, now I've put this little half arrow up here above torque, and you know that that indicates it is a vector quantity, so that means it's got magnitude and direction. Well, we just figured out how to get the magnitude. We're going to use the equation to get the magnitude. So now we got to figure out how to come up with the direction. The way you do that is by using the right-hand rule. Now there are a couple of things that students usually let get in their way when they're using the right-hand rule. First off, you got to know which one is your right hand. Okay, so that's the hand that doesn't form a correct L shape. It's a backwards L, all right? So like a right angle. Okay, so find the right hand, and then the next one is that sometimes you're too cool to use the right hand rule. You're going to look weird when you use this. You're going to have to move your hand all around. You're going to have to twist your arm in weird directions. And a lot of times you don't like looking weird in front of other people, so you just go ahead and decide to get the question wrong. because you're not willing to use the right-hand rule. You're going to have to get over that. Everybody's going to be doing it, so you got to do it too, and nobody will look weird. You're going to look weird if you're not doing it, okay? So be willing to move around so that you can get your question correct, all right? All right, so here's how you do the right-hand rule. Step 1, you're going to place your hand at the axis of rotation. So if this is our example down here, you're going to put your hand over the top of the axis of rotation. Then you're going to point your fingers along the lever arm. Now remember, the lever arm is the distance between the axis of rotation and the force vector, right? So this right here is the lever arm, and you should be pointing your fingers in that direction along the lever arm, okay? Then you're going to curl your fingers in the direction of the force, okay? Now you cannot curl your fingers backwards, against your knuckles is what I'm talking about. So if we're pointing our hand, you mind draw a little hand here. We're pointing our hand in this direction so that our fingers are pointing along the lever arm, and let's see, these are my knuckles there. I can't curl my fingers in this direction because I would break my knuckles. So what you're going to actually have to do is turn your hand upside down, all right? Then you can curl your fingers as they normally would in the direction of this force vector, okay? Now, when you do that, your thumb will be pointing in the direction of the torque vector. So if I do this correctly, then my thumb is actually going to be pointing into the page or into the board, all right? So my torque vector points into the board, and into the board is going to be a clockwise rotation. If we look here, if this door were to spin around the axis of rotation, this force here would cause it to spin in a clockwise fashion, okay? So clockwise fashion means that the torque vector points into the board, and that is going to be considered a negative sign, okay? So just like when we started out physics, we said that, things that move to the right, that's positive. Things that move up, it's positive. To the left is negative. Down is negative. Forward is positive. Backward is negative. Okay, so we have to establish our coordinate system for clockwise and counterclockwise, okay? So clockwise rotation is going to be negative. This comes from the unit circle again. This is 0 degrees, this is 90, this is 180, and this is 270. As you head around the circle in this counterclockwise direction, the values increase. In other words, they become more positive. If you were to work your way around the unit circle in this direction, the values decrease. Okay, so they're heading in a negative direction, you could say. All right, so a clockwise rotation is going to be negative, and a counterclockwise rotation is going to be positive. And in that case, your thumb would be pointing out of the board. Okay. All right. Let's see if we can figure out what the sign of the torque value would be here. Okay. We don't have any numbers, so we're not getting a magnitude. We're just going to determine the direction here. Okay. So if you point your fingers along the lever arm, curl them in the direction of the force, then you're going to get this clockwise rotation. Your thumb is pointing into the board, so you should get a negative value, right? Negative value, and we'll call that clockwise rotation. We're going to use the right-hand rule here to figure out what the direction of the torque is for example number 2. All right, so what's the first step to doing the right-hand rule? Yeah, find your right hand. And where are we going to put our right hand? On the axis of rotation. So let's do that. Then what do we do with our fingers? No, you don't. Point them in the direction of the lever arm, which is pointing which way in number 2? To the left. So let's point our fingers down the lever arm. Then what do you do with it? Curl them in the direction of the force. All right. So our thumb's pointing which way? Out of the board. All right. So it's going to be what? All right. That's going to be positive, which would give us a counterclockwise rotation, all right? But the torque vector itself is pointing out of the board, so that would be a positive torque. Good. All right, so that one we'll say is positive. And that one is counterclockwise. Okay? All right, now I want you guys to try number 3 on your own and raise your hand when you think you've got it. All right, Cassie, tell us what you came up with, please. All right, so what sign is that, positive or negative? Negative, very good, okay? This is negative, and that's going to be a clockwise spin. Very good, okay? Awesome. All right, now do number 4 and raise your hand when you've got it. All right. Brady, tell us what you come up with, please. All right, Brady says it's positive, and that's what? Counterclockwise. And which way does your finger point? I mean, your thumb points. Very good. Out of the board. Okay, number 5. Try number 5. Okay, Mark, tell me what you came up with, please. Okay, the vector is outward. Okay, and so what does that mean? What's the sign? Positive. And what's the rotation? Counterclockwise. Very good. Okay, now y'all try number 6, please. All right, Garrett. Very good. There's no torque here. Okay, notice that the force vector here, the force vector is 180 degrees from the lever arm. So if you were to take the sine of 180, well, what would you get? 0. So there's no torque, right? Well, there's none at all. Yeah. Okay. All right. So let's copy this question down and work it. All right, find the magnitude of the torque produced by a 3.0 Newton force applied at an angle of 60.0 degrees to a door 0.25 meters from the hinge. What is the maximum torque this force could exert? So let's go through and see if we can't work this out. Okay, so we've got our axis of rotation down here. Where's my lever arm? Very good. So right here's my lever arm. So let's kind of fill that in. All right. And then I need an angle, right? So what is the angle theta by definition in the torque equation? Very good. Between the lever arm and the force, right? So here's my lever arm. There's my force vector. So I need this angle right here. So that one's going to be 120 degrees, okay? Now, there's actually 2 ways that you could have drawn the picture described by the problem setup, okay? We could have had a door that looks like this if we want to. And we could okay? That picture also satisfies all the requirements from the problem, okay? Which is why the question only asks you for the magnitude and not the magnitude and the direction, because depending on which way you interpret a problem on a test or quiz or something, you may end up drawing a different kind of force, all right? So you may have drawn your force pointing in a different direction. Now the magnitude is going to be able to be the same because the sine of 120 and the sine of 60 are the same number, right? Okay, so let's go ahead and plug some stuff in then, all right? What's my torque equation? Thank you. All right, so now let's go ahead and plug stuff in. So we've got a 3 Newton force. What's the lever arm length? 0.25 meters. And then we'll say times the sine of, and I'll just do 120, okay? All right, so type that stuff in. How many sig figs should our answer have? 2. All right, so raise your hand when you know the answer. Isaac? 0.65 Newton meters. Okay, 0.65 Newton meters. Is that what we came up with? Yeah. All right. Well, now let's make sure that we've actually answered the question. Okay? The question said, what is the maximum torque this force could exert? Okay? Now, how can we come up with maximum torque? What has to be true, Josh? Yeah, it must be at 90 degrees, okay? So if you were at 120 degrees, this is the torque you would get, but we were asked what would the maximum torque possible be, all right? So we need to go through and figure that out. Pretty much you just look for sine theta. Yeah. So just be 4 times the point. But so when it says this force, the angle isn't included in the force. No, it's included on the force. So that would be. All right. So what do we come up with then? 0.75. Is there ever a thing that Newton meters divided by? All right. So we've got what is actually going to happen up here, the 0.65 newtons. But if the person adjusted their angle so that it was 90 degrees, then the maximum torque that they could get out of that 3 Newton force would be the 0.75 Newton meters down here. Next question here. What is the net torque on the door pictured below? Include magnitude and direction. All right, so take a minute and draw that picture. Okay, so if we're going to calculate the net torque on something, okay, then we're going to have a torque caused by force 1, we'll have a torque caused by force 2, and we'll have a torque caused by force 3, correct? All right, so then that means that our net torque is going to be equal to torque caused by force 1 plus torque caused by force 2 plus torque caused by force 3. Correct? Okay. Now, torque is a vector, which means we'll have to take into account the direction of each of those individual torques, okay, so that we can get the correct sign in there. All right, let's do the torque because of force 1, okay? So let's see here. Torque caused by force 1 is equal to, what is force 1? All right, it's going to be 30 newtons times, what's the lever arm for force 1? 0. Very good. So 0 for torque force 1. All right, now let's do the torque caused by force 2. So what is force 2? 25 newtons. What's the lever arm? 2 meters. And what's the sine of the angle? All right, so they said it was 121. Now remember, this right here is 90 degrees, right? And we need the angle between this force vector and the lever arm. So we need that 90 plus that 31 to get a total of 121 degrees. Does that make sense to everybody? Okay. Yeah, if this is your lever arm right here, okay, and then we've got our force vector right here, then the angle between those is this right here, this amount. So it's 90 plus 31. Okay? All right. So what do we come up with for torque 2? Anyone? No. 42.85. Yep. 836,504. That's a naked number, Brady. Nope. No, wait, shoot. I know it. Hang on. Newton meters. Very good. All right. Now let's do the torque caused by number 3 there, by force 3. So what is force 3? 10 newtons. What's the lever arm going to be? 4 meters. And then what is the angle theta going to be? All right. Okay, let's talk about how we came up with 157 for those that need it. Okay. Again, if this is your lever arm and this is the force vector, then what we are actually looking for is this angle right here. Okay. If we say that this entire angle here is 180, then all we have to do is back up by 23 degrees, and that would give us the piece that we're looking for, right? So you'd say 180 minus 23. Okay, so type that in, and let's go ahead and get our torque value. Desire? Yes, please. Very good. Okay, now we just need to add up our individual values here, but we have one more thing that we really need to do before we can start adding them. Yeah, we need to do our direction, okay? So go back and look at your picture, use your right hand rule, and figure out what the sign is for torque 2 and torque 3, okay? What do we come up with? What do we say for torque 2? What's the sign going to be? Positive. What about torque 3? Torque 3 has to be a negative value, okay? Good. So I'm going to come in here and put negative 15. And now when I'm adding these, it's really subtraction. So my net torque then is going to be the 42 number minus the 15 number equals what? 27.229. Well, let's do sig figs now. 27 Newton meters, and this is what sign does the net torque have? It's a positive value, so what's the rotation? Counterclockwise. All right, so my net torque then is 27 Newton meters counterclockwise. If we don't write counterclockwise, is it okay? Yeah, if you don't write counterclockwise, then that's what I will assume because it's a positive value. All right, so always make sure you double check your directions there. Questions? All right, cool. Then that's the end.